In this lesson, we're going to talk about the uncertainty and measurements that you may take with your instrument. So you're going to learn what uncertainty is and why it is both analog and digital instruments have uncertainty with it. Now, what is uncertainty? Uncertainty is anything that you're unsure about or you have doubts about. And just from the definition alone, it should give you a hint as to what this would tell you. You are going to be uncertain, or you're going to have doubts about the readings that you take. And this is natural and normal when you're doing physics. Every time that you do a measurement in physics, you must always state the uncertainty along with the value that you have, and you will find out how to figure out what uncertainty you have in the instrument. Alright? For in this case here, we see that in an analog instrument, when you go between graduations here and here, or each one successive one, you would see that this here speaks of uncertainty. We are not certain about what those values are. However, on the graduations itself, we are certain as to the value that it have. Notice, however, that we can either be a little more than half or a little less than half. So what we say the uncertainty is for an analog instrument is to take the smallest graduation we have, and in this case we see that the smallest graduation represents 0.1 of a value. So you take the smallest graduation, you divide it by 2, and when you divide it by 2 you get the value of 0.05. And what you're going to do in this case is that you're going to say that whatever value it is, let's say for instance we read off some value here, we read off 2.3. If we read the value of 2.3, then we have to state it with the uncertainty plus or minus 0.05. And that simply says we are unsure about the value of 2.3, but we know that it lies a little bit, we know that it lies within the range. It's going to lie somewhere here. That we are sure about. It's going to lie inside that range. And that is what this plus or minus tells us. We know that it's going to lie in between here. So if we state in 3, the uncertainty states that within this little piece of range, notice that we can see that the 3 lies inside of there. When you're looking at a digital instrument, the uncertainty is just simply with the number of decimal places or the precision that the instrument has to offer. Say for instance you're measuring the mass of an object, and this object has a mass that is to 3 decimal places. Say for instance, to 3 decimal places. Let's say for instance there it may lie between 12.295 and it may lie between 12.304. Notice that in between these values, this last decimal place here that you have is always going to be rounded off, and the answer will still be the same of 12.30. And it brings up the same thing. It brings up the same kind of way of finding the uncertainty. Simply take the smallest precision that you have, which is this here, 0.01, and divide it by 2. And then simply look at it, you'll get 0.005. And when you take the 12.30 and you minus the 0.005, notice this is what you get. And when you actually plus the 0.005, notice this here is not what you get, but you would see why it is the value of 4. Alright? Now, this brings in a little bit of confusion. It simply asks, is it that your reading is incorrect? And is the reading that you're really correct then? And the answer is yes, the reading really is correct. Alright? We are just simply stating the uncertainty to account for the fact that the instrument may have a little bit of error in it when it was calibrated. Alright? So we're saying yes, the reading is correct. And when you look at it in terms of a larger scale, let's say for instance we're measuring the size of a football field, we are not going to actually take the football field, the millimeter readings at the end of how many of meters that we get for that football field. Or let's say we measure a field and it gives you 200 meters. You're not going to try and find out how many millimeters beyond that 200 it is. You're just going to simply state the meters part of it. So that's why I said yes, the reading is correct, and it's relevant to whatever it is that you're using the instrument to measure, what quantity you are measuring. So when it is relevant to take millimeters, you take millimeters, and when it's not relevant, you don't bother with it. Alright? So let's say for instance you get the next question. The next question is how you should go about writing it. Alright? So to write these questions, what you simply have to do is just simply follow this little rule down here, and it may look a little bit troublesome right now, but let's simplify it. Earlier on we said that we had a value of 2.3. Alright? Let's actually go with the one 12.30 because we was unsure about that. So we had the value of 12.30, and we said if you plus the error, so if this is the case of x, and if you plus the error and minus the error, so I'm going to write this as delta x, the little triangle that you see in there, the error that we saw, the uncertainty, sorry, that we saw was 0.005. Alright, so if we plus and we minus it, we notice that what we got was 12.295. We have our 12.30 here, and we have the 12.304 here. Sorry, 5 here. Alright, notice the symbols now in between this notation here. This says it must be that this value here must be less than or equal to this value here, and that is ideally the case that's going on right now. Now when you look at this, we see that this value here must be less than this value over here. Now it cannot be equal to 12.305. Notice that a value less than 12.305 to 3 decimal place is the 12.304. So we can start from there and go downwards. But we are counting for values where it has more than 3 decimal places. Say for example it has 12.3042. Notice that is still less than 12.305. So if you have any questions or comments about this video, if you find anything unclear and you need help with it, just simply send me a message and I will get back to you as soon as I can. Thank you.